Good evening, everybody. Welcome to Chem 170 with your host, me, Dr. White. Hi, everybody. Before I get into test number 4 review, I'd like to remind you, one, hand in your labs. It's getting to the end of the semester. Hand them in. Two, remember the extra credit project, which is optional, but I highly recommend you do that. The deadline for that is this Thursday, the 1st of December. So make sure if you want to do it, get it in on time. And with that, let's start with the review now with test number 4, which is this Thursday. I'll be giving it online. Now, first of all, let me remind you that because of I don't know if you call it design flaw or whatever, some of the things near the end of the lecture folder in D2L, you may have to hit at the bottom the more button or see more, whatever it says, so you can see things like test 4 review. All right, let's start. First part, polymers. You should know what is the definition of a polymer. And a polymer is a macromolecule, that means a huge molecule made up of repeating units called monomers. Now, when we talk about polymers, one way to distinguish them is by a certain chemical property. And those are two different types. One is addition polymer, the other is condensation polymer. Now, an addition polymer, you should know, is a polymer with only one type of monomer. It's like a repeating freight train where all the boxcars are the same. If you watch the video, you know Dr. White loves trains. I do model railroading. Oh, my father got me into it. And so an addition polymer is a polymer with only one type of monomer. And you should know an example of an addition polymer. A rubber tire is an addition polymer. The plastic wrap, and I use the brand name Saran wrap, but all plastic wrap used in the kitchen is an addition polymer. Now, the other type is a condensation polymer. And a condensation polymer is where you condense, bring together two or more different types of monomers to make your polymer. Oh, I better not put this away. What's an example of a condensation polymer? My water bottle. The plastic here, this is a polyester made by a polyalcohol, with a polycarboxylic acid or also a polyacid chloride. Now, those are two ways of classifying a polymer by chemical properties. A other way is by a key physical property to identify different types, two types of polymers. And one of those that you should know is a thermoplastic polymer. Once formed, it can be reheated and reshaped. In other words, recycled. And examples of that, again, my plastic bottle or the saran wrap. There's no correlation between the chemical type and the physical type. Now, the other type of physical property used to designate types of polymers is a thermoset polymer. Now, once formed, it cannot be reheated or reshaped. Once you make it, you're stuck with it in that form. You can't really, it's really hard to recycle. Example of that are rubber tires, also urethane foam, like the cushion you sit on your car or the insulation of your refrigerator or your home even. And that's polymers. Next, I went into fats and oils. And we have what's called a lipid. And a lipid is a molecule from plants and living things like us that are soluble in nonpolar solvents, but not in water. Now, there are two types of lipids, saponifiable lipids and non-saponifiable lipids. And you should know saponifiable lipids, also called fats and oils, yield carboxylate anions plus other things in a reaction with base and water. In other words, saponification of an ester. We'll learn later on, or you've already, if you watched the video, fats and oils are triesters. Three esters. Now, the other type of lipid is non-saponifiable lipid, and that does not react with base and water, that type of lipid. And you'll learn later on, those are called our steroids, our hormones. All right, now, you should know what's a fat. A fat's a solid or semi-solid triglyceride at room temperature, and an oil is a liquid triglyceride at room temperature. So if you go and make a hamburger or bacon, and the fat left in the, say, made in a frying pan, once it cools down, it solidifies because it's a fat. But if you pick up at room temperature a bottle of vegetable oil, it will be a liquid because it's an oil. Now, the general structure for triglycerides is this triester. And here's ester number 1, ester number 2, ester number 3. Now, the fats and oil chemists, which is not what they're called, but I'll use that term for you, write their ester, or general organic chemists, synthetic organic chemists, write it this way in ester. But fat and oil chemists write it this way. Sort of flipped, and they changed the R and R prime. So like in this one, here's our carbonyl, and here's our ester. Same thing the others. Now, good news. As I promised at the end of the chapter on amines and amides, no new really chemical reactions, sort of. Well, you already know what happens when you react an ester with acid and water. You break it down, acid hydrolysis and ester, you get back the alcohol and the carboxylic acid you would have used to make that ester. Well, if you have a fat or oil, you have this triester, also known as a triglyceride, acid and water. The first ester forms this alcohol plus this carboxylic acid. Next ester forms this alcohol plus this carboxylic acid. And the third and final ester forms this alcohol. They're all together. And this is called glycerin. And you form the last carboxylic acid. And that happens in your stomach. And at chemical plants, we work this or a similar reaction. I worked that for a number of years where I was laboratory manager, in charge of quality control and research in all of North America, that we made glycerin. Our main products were fatty acids, these carboxylic acids from, and we use mainly animal fat because it's a lot cheaper than vegetable oil, a lot cheaper. And glycerin. And we used to make a couple million pounds of each every week. Yes, every week. Now, you also learn for test number 3, base hydrolysis of an ester. And when you take an ester, react with sodium hydroxide and water, remember sodium hydroxide is a base, you get back the alcohol you would have used to make that ester, plus because you're in base, the carboxylic acid you get immediately reacts to give the carboxylate anion. Therefore, if you have a triglyceride, a fat or oil, react with base and water, you get back glycerin. This ester gives you this alcohol plus this carboxylate anion. This ester gives you this alcohol plus this carboxylate anion of the carboxylic acid you would have used to make that ester. And the final one gives you this alcohol. And again, you get glycerin plus this carboxylate anion of the carboxylic acid you would have used to make that fat or oil, this ester. And this is called saponification because these carboxylate anions of fatty acids are also known as soap. We'll talk more about that in a little while. Now, last one, this is I worked at a company and we use this reaction a lot. You take an ester and react it with steam. What is steam? Hot water. And if you think about it, how do you make a reaction go quicker? One is use a catalyst like an acid or base, like we just did. The other way is increase the reaction temperature, run it at a higher temperature. For most reaction, when you double the temperature, for every 10 degrees C increase in reaction temperature, the reaction rate doubles. So if you use hot water instead of regular tap water or cold water, it goes quicker. And if you use steam, you can use high pressure steam, which is very hot. You get that on that, it can kill you if you're not careful. That's how hot it is. You get the same reaction products as acid hydrolysis. You get back the alcohol plus the carboxylic acid you would have used to make that ester. So if you take a fat or oil, this triglyceride reacted with steam, first ester, you'll get this alcohol plus this carboxylic acid. Second ester, you'll get this alcohol plus this carboxylic acid. And third ester, you'll get this alcohol. In other words, you get glycerin plus this carboxylic acid. Now, these carboxylic acids that come from fats and oils are called fatty acids. And fatty acids play an important part in our life, not only in your body, but also in the chemical industry, because I worked for a company that made these. Like I said, it was Unichem Chemicals. It was still located at 47th and Racine. They've changed their name, and I think they've been bought by someone else. But that plant in Chicago, we start with about 2 to 3 million pounds a week of fats to make glycerin and fatty acids. Now, I'm going to ask you to learn the names of the two most important, at least for me in the chemical industry, fatty acids. The first one, you should know the structure. Hint, know the name, know the structure. First one is stearic acid. Stearic acid is a saturated fatty acid, only carbon-carbon single bonds, and it has 18 carbons, 16 here, 16 CH2s, plus 1 here, plus 1 here, 18. The other one is oleic acid. And oleic acid also has 18 carbons, but at carbon number 9, this is 1, plus 7 is 8, this is 9, there's a double bond. And that double bond can be cis or trans, and that's oleic acid. If you look in some of the products, if you see stearate or oleate, those are molecules made from stearic acid or oleic acid. Look at a lot of your personal care items like hand lotion, skin creams. They have a lot of stearic acid derivatives and oleic acid derivatives. Now, when it comes to fats, there's two types: saturated fat and unsaturated fat. And saturated fat, you should know, only has carbon-carbon single bonds. Both have a carbonyl, which is a carbon-oxygen double bond, but as in stearic acid, which is a saturated fatty acid used to make saturated fats, there's only carbon-carbon single bond. Now, unsaturated fat has at least one carbon-carbon double bond. Mother Nature never did triple bonds. That's something organic chemists came up with. So you should know, saturated fat, only carbon-carbon single bonds. Unsaturated fat, at least one carbon-carbon double bond. Now, since I worked in this industry, I can teach you stuff that's not in the book, and that is you should know the chemical industry we call beef fat tallow. We call pig's fat, there are two types, yellow grease and white grease. And I think I told the story in one of the videos where I was asked by the president of the company, United States, because we were part of an international company, to help secure that, because it was very expensive in Europe and cheaper in the United States at the time, the shipment of 1 million pounds of tallow from New York to Rotterdam, the Netherlands. And I worked with the purchasing agent to make sure high quality stuff was shipped. And when it arrived, it was still high quality stuff. And that was fun. So you should know beef fat, tallow, pig's fat, yellow grease, and white grease. Now, to give you a real life experience of what's happening when you work with tallow, yellow grease, and white grease, I came up with the following approximation, because all three are about the same. You can interchange them. We did. Usually yellow grease and white grease is a couple of pennies a pound cheaper than tallow. And if you're buying 100 million pounds a year or more, that adds up. But at times it's hard to get, so you go with the tallow. And the designation I did here was this. You have your triglyceride, and two of them are R sub S, where when you hydrolysis the fatty acid you get would be stearic acid. And one of them, R sub O, the fatty acid from the hydrolysis of that would be oleic acid. Now, if I ask you to draw the structure of oleic and stearic, don't use the abbreviation. Draw this out like this. But if I ask the following reaction, say, give the organic product or products for the reaction of tallow with sodium hydroxide and water, and I also tell you get 3 different products, what do? Well, tallow, you should use this designation, and you should know that. It's a triglyceride where 2 of the R groups is R sub S and 1 is R sub O. And you should know it's a triglyceride. And if you take, oh, by the way, I forgot I had a brain freeze, but people working fats and oils are called oil chemists, and people work with crude oil are called petroleum chemists. That's the difference. I was an oil chemist, and I still do consulting in that area. But you have a ester, base, and water. You get back the alcohol plus the triglyceride. I mean, you get back the carboxylic acid. No, the carboxylate anion, because you're in base of the carboxylic acid you would have used to make that. So if I ask, What's the reaction products of tallow with sodium hydroxide and water? You would get first ester, this alcohol plus sodium stearate. Second ester, this alcohol plus sodium oleate. And the third ester, you get this alcohol and you would get sodium stearate again. You don't have to write the two here because I never ask you to balance. And therefore, there are three different products. You should know the same reaction instead of sodium hydroxide, if I had acid and water, or if I put steam here, what would be the products? All right, next, one of the most important things you should know leaving my class, how does soap work? You should know what's the structure of soap. And the structure of soap is a nonpolar tail, polar head. You should know, and I don't have down here, but I better put it down here. Water is polar. I can't spell. I think I told you long ago, I was always first one down as spelling bee, still would be. But anyways, and dirt and grease are nonpolar. And there's a very important rule of thumb. See, it's always hurting on this thumb. Can you see it? Oh, it's bad humor night. But anyways, is like dissolve like. And that's the key to the puzzle, how soap works. Like dissolves like means things that are polar are soluble in polar things. Things that are non-polar are soluble. If you put polar and non-polar together, they're not soluble. Just look at oil vinaigrette dressing. Vegetable oil and oil vinaigrette dressing is non-polar. The vinaigrette is vinegar, acetic acid and water, mainly water, so that'd be polar, and they separate after you put the bottle down, after you shake it down. My mother liked Wishbone Italian. Years later, unfortunately, after she passed, I learned how to make my own much better, and that's what I use. If you want to make really good Italian dressing, use, instead of regular vinegar, use Japanese rice wine vinegar. Marucan is the best. And put in your seasonings, and ooh, it's dangerously good. But anyways, the key to the puzzle is like dissolves like. Here we have dirt. Dirt is nonpolar. The nonpolar tails of soap molecules are attracted to the dirt because of like dissolves like. But the polar heads stay as far away on the outside. And you should know this forms a micelle right here. Now, the micelle, now I don't have a picture, but if you go back, I have a nice one, chapter lecture notes or slides. The micelle looks polar to water because the whole dirt is surrounded by the soap molecules with the polar heads on the outside. And the micelle looks polar to water, and water says to the micelle, I'm polar, you're polar, like dissolves like, let's go down the drain together. And they do. And that's how I got my hands clean. Or if you washed your hair, your clothes, your dishes, took a shower, whatever, a bath, that's how you do it. And liquid or bar soap both have this general structure, and you should know this. Now, next thing I talked about non-saponifiable lipids, otherwise known as the steroids. And those are your hormones. And they all have this basic fused, that means connected, 4-ring skeleton. And you should know how to draw it. You have a 6-membered ring. Next to it is a 6-membered ring. Up here is a 6. Over here is a 5. Whatever hormone in your body has that structure. There are other things on it, but that's the basic building block for all our hormones. Male testosterone, female progesterone, all have those, and you should know how to draw the structure. Next, we got into something sweet and fattening. Like, I don't need that. But anyways, carbohydrates. And you should know a carbohydrate is a polyhydroxyaldehyde or polyhydroxyl ketone. Poly means many, hydroxyl, you know that, OH on a carbon, you know what an aldehyde and ketone are, or molecule that upon hydrolysis, adding water under certain catalytic conditions, like acid, become a polyhydroxyaldehyde or polyhydroxyl ketone. Now, when we talk about carbohydrates, you should know they exist in different forms, like your right and left hands. And we call that chirality. And you should know that chirality means handedness in Greek. And it's been a couple of years ago. It turned out one semester I had not one, but two students who are from Greece. Obviously, they spoke Greek. When I said that, they said, yep, you're right. That's what it means in chiral handedness or hand. So you should know the definition of chirality. Now, there are two types of objects. One is an achiral object and the other is a chiral object. Now, I'll never ask the definition of achiral or chiral, but you should know how to identify whether an object is chiral or achiral. And an achiral, A means without handedness, is an object with a superimposable mirror image. And a chiral object is an object with a non-superimposable mirror image. And that's how you do it. Now, here's a secret. If you see in the name of a object, left or right, immediately you know it's chiral. If you don't, you got to do the mirror image test. But if you see, like, I put on when I went out today, because it's really cold out today, like about 20 where I live, earlier this afternoon, I put on my left glove, winter glove, because I put it on my left hand because my left winter glove is chiral. So is my right winter glove. It wouldn't if I put it on the wrong hands. By the way, left hand, right hand, your hands are chiral. All right, next, I talked about chiral carbons, atoms. And I'll never ask you to define on a test what is a chiral carbon, but you should be able to identify chiral carbons in a molecule. And a chiral carbon atom is a carbon atom with 4 different groups, 4 different atoms, or a combination of 4 different groups or atoms. Now, along this time, I showed you the Fisher structures named after Dr. Emil Fisher, who also did Fisher esterification, how to make esters. And a Fisher per structure projection would be, this would be an example. And each intersection here of a line, there's a carbon. Now, this H and this OH are coming out to you, and this carbon are going back. So this is a Fisher projection, and that has 4 carbons. If you notice, this carbon right here has a hydrogen, OH group, an aldehyde, and these 3 carbons with hydroxyl groups. So that would have 1, 2, 3, 4 carbons, and that would be chiral. And turns out this would be chiral, this would be chiral. This one is not, because if you have 2 or more hydrogens, it can't be chiral. This carbonyl carbon can't be a chiral carbon, because if a carbon is in a double or triple bond, it can't be chiral. Now, next, I asked you to know about enantiomers. What is an enantiomer? A non-superimposable mirror image of a molecule. So your hands are enantiomers, they're non-superimposable mirror images, and they're not superimposable. So if I were to ask you to draw the enantiomer of this molecule, what do? Well, that means you got to draw the mirror image. And I like to put my mirror in. You have your backbone, then this carbonyl. Now, this carbonyl is not a chiral carbon, so I really don't have to draw the mirror image. Same thing here. And organic chemists are lazy. I am one. Now, if we look at this first carbon here, whatever closest to the mirror, you'll see the reflection closest first. So here, the hydroxyl group is closest, and the hydrogen follows farthest away. This one, same thing. What's closest to the mirror, you'll see first. What's farthest away, you'll see farthest away from the mirror in the reflection. Same thing here. What's closest to the mirror, H, farthest away, OH. This one, H, OH. Now remember, with a Fisher projection, you just can't pick it up and flip it over. You can't, because it has stereochemistry, just like a car. If you flip it over, this way the wheels are down. When I flip it over, now the wheels would be up. It's not the same. So you can't, the only thing you can tell if it's superimposable or not is if you pick it up and display it over, and they're not. So this is the answer right here. And that's how you do an enantiomer. Now, when it comes to working with carbohydrates or simple sugars, which are monosaccharides, a reaction you'll learn for test 2 is if I take an aldehyde or ketone, react it with an alcohol in the presence of acid, you get this hemiacetal or hemiketal. This alcohol attacks the carbonyl carbon and opens it up to this hemiacetal. Now, when the molecules, the functional groups are in the same molecule, you don't need a catalyst, but they're reversible. And that's why I have this equilibrium right here. And here on carbon 5 is the hydroxyl group of this alcohol. Here's my carbonyl. Do you break carbon-carbon single bonds? No. So I'm not going to. So I can redraw this. The only thing that changes is this oxygen, which is this oxygen, which is this oxygen, bonds to that carbonyl carbon, opens it up with an OH on it. And you should know how to do this. If I give you, and this one is for glucose, I will never ask you what's the structure on glucose, but it helps to be familiar with it. This is the cyclic form of glucose, called a glucoside, I think. I won't ask that. You start with fructose, which has a ketone, same hydroxy group on carbon 5, same reaction, form a hemiacetal, the carbonyl, which is this carbon right here. This oxygen here is bonded to this carbon, which is this carbon, with an OH, and this is fructose. If these two reactions didn't happen, especially the first one, we wouldn't have any carbohydrates or starches in our life. You know, the good stuff, potato chips, French fries, pizza, oh, never mind. All right, now, when you have the hemiacetal, here's a slightly new reaction, slightly. When I gave it in class for test 2, use 2 alcohols to make the acetal or ketal. But if you take and stop at the hemiacetal, you can react not the same one, but a different alcohol with the hemiacetal to form the acetal. And here, the hemiacetal, I'll ask you to learn, is this one. And this carbon right here is this carbon right here. And the only thing that changes is this OH becomes this OR triple prime. And same thing, this OH becomes this OR triple prime. And you should know that. Now, why is this? 2 things you should know. What is sucrose? That's table sugar. That you should know. The white granular solid you put in your coffee, tea, or when you're cooking to sweeten things up. And you should know it's made up of fructose and glucose bound together. Now, starch is a polymer of glucose. I didn't ask you to learn how to do what I showed in the video, but glucose molecules come together via this type of reaction. And therefore, the functional group in starch is an acetal linkage, which I'll talk about in a second. Now, key carbohydrate reactions. You take a lot of glucose and react with acid, you'll form starch. You'll link them together in this type of reaction right here. And the linkage between starch between glucose molecules is an acetal linkage. And same thing in sucrose. So in your stomach, where there's H plus acid, hydrochloric acid, and water, by the way, I better put some more in there. Sucrose breaks down to fructose and glucose, and you should know that. Now, starch breaks down your stomach to glucose. And both in our and animal stomachs, when we eat any starch, we make glucose, and glucose is the sugar that's in your blood that does things that I don't know about because I'm an organic chemist. I don't know those things, not well. All right, now, something you should know leaving my class. You should be able to describe with words and a general reaction what happens when you eat a fat or oil. What is the functional group in a fat or oil? An ester, you should know that. And what's in your stomach? Acid, water. So when you take an fat and oil and ingest it, those esters in your stomach undergo acid hydrolysis of an ester. And the general reaction that you learned for test number 3 was an ester plus acid and water. You get back the carboxylic acid plus the alcohol you would have used to make that ester. Again, you should know how to describe with words and a general reaction what happens in your stomach when you eat a fat or oil. And that's acid hydrolysis of an ester. And here's the general reaction. Next, leaving my class, you should know what happens in your stomach, mine too, when you eat a carbohydrate. And what's the functional group that holds glucose together in starches or carbohydrates? An acetal function. So that's acid hydrolysis. Remember, water and acid, your stomach, acid hydrolysis of an acetal. And you learn for test 2, acetal or ketal, acid and water, get back the aldehyde or ketone plus the alcohol you would have used to make that acetal or ketal. Now, this turns out that when it happens in your stomach, both of these are in the same molecule and you get back glucose. But you should know how to describe with words and a general reaction what happens in your stomach when you eat a carbohydrate. And the functional group that holds glucose molecules together in a carbohydrate like starch, or even sugar, fructose and glucose held together, is an acetal linkage. And there's acid and water in your stomach, therefore it undergoes acid hydrolysis of an acetal. And here's the general reaction. And finally, one last thing I'd like to go over again once more. Was that important? How does soap work? You should know the structure of soap. Nonpolar tail, polar head. Water's polar, dirt and grease are nonpolar. And the most important thing, the key to the puzzle, how soap works, is like dissolves like. And because of that, the nonpolar dirt attracts the nonpolar tails of soap, but the polar heads want to stay far away. So they surround the dirt to form what you should know is a micelle. And a micelle now with the polar heads totally surrounding the dirt looks polar to water. And water says to the micelle, you're polar, I'm polar, let's go down the drain together. And they do. And that's how you get your hands clean, like mine. Yep, they're clean because I use soap and water. And the soap knew about like dissolves like with the dirt. And while I'm here, don't forget, here's the structure of a ring skeleton you should know. And this reaction, you should both know this equilibrium to form the cyclic form of glucose or the cyclic form of fructose. I might ask you, give the starting material for this reaction or this one, or I'll put this, give the product. So you have to understand that. But this is chemistry we did for basically test number 2. And as I said, leaving my class, you should know how to describe with words and a general reaction. First, what happens when you eat a fat or oil? You describe that, what functional group is in a fat or oil, and ester. And because there's acid and water, that's acid hydrolysis of an ester. What's the general reaction? Ester, acid, we use H plus to show on the acid. H2O, I hope you all know, is water. Oh, I hope you do. You do. And you get back the carboxylic acid and the alcohol you would have used to make that ester. And finally, you should also know, leaving my class, hint, you should know how to describe with words in a general reaction what happens when you eat a carbohydrate. And there, again, in your stomach, there's acid and water, excuse me, and I'm getting all choked up over this good stuff. Oh, that was lame. Sorry. But anyways, acid hydrolysis, and what's the functional group that holds glucose together and starches most carbohydrates? And acetal linkage. And the general reaction you learn for test number 2, acetal or ketal, acid and water. You get back the aldehyde or ketone plus the alcohol you would have used to make that acetal or ketal. And with that, I'm done. Don't forget, extra credit project deadline 12/1/23. I'm done. Don't forget, Thursday, I'll be giving it starting at 8 a.m. I'll send out the password for test number 4. And with that, I'll say, gang gesund. Remember, that's Yiddish for going hell. And watch out, flu is starting to spike, especially on children. I already had my flu vaccine, about 3-4 weeks ago. I also had my latest COVID booster. And later this week, I'll be getting my RSV vaccine because if you haven't noticed, I'm over 60. Yep. Anyways, gang gesund. Bye now. I stole that from Granny to Beverly Hillbillies. Bye.